Our next topic is going to be electrical potential. Now, electrical potential is maybe going to sound a little alien at first to you, but I guarantee you all of you have used the concept of electrical potential before in your life. And here is how I know. The unit for electrical potential is the volt, capital V. Okay? That's 1 joule per coulomb. But I know you've all used joules, or volts rather, before. You have 9-volt batteries, you have 12-volt batteries. But what does that mean? The volt is a measure of how much energy a particle gets by going from one end of a field to another. So if we have an electrical field, okay, it's got some strength E, and I let a charge go ahead, call it plus Q, go from one end of E to the other. In going over this distance, it's going to gain a certain amount of energy, okay? So the change in potential energy here, well, let's think about what we know. That's force times distance, okay? Well, sorry, the negative of the force times distance, because we're talking about the potential energy lost in this case. Okay, but what's the force? The force is QE. So we get QED, the minus sign, okay? So that would be the energy we'd gain for that charge Q. But if we came back and we put a different Q in here, maybe big Q, we'd get a different equation over here. And that's not okay. We really like having these things that are independent of the charge that's moving through the field. So what we do is we define potential, which has the same symbol as the volt of a capital V, to be the potential energy over the test charge. And we throw a minus sign in because you're decreasing potential energy as you're gaining kinetic or thermal or whatever else it's turning into. So what makes that interesting? Well, for example, a 9-volt battery, if I draw one here, badly, okay, if I connect up the two leads, okay, and I send a single positive charge from one to the other, okay, well, this is 9 volts. That charge gains an amount of energy that's equal to 9 volts times whatever that charge is, okay? So if it's one positive electron charge, for instance, it's 9 volts times 1.6 times 10 to the minus 19th joules. Okay? If I send one electron over, which would go the other direction, obviously, that's also negative 1.6 rather, times 10 to the minus 19th coulombs times 9 volts, which is whatever the multiplication. I can't do the math in my head. But it has another name, by the way. If we send one electron over 1 volt, that's 1 electron volt. Oh, hey, that's where the electron volt came from on our equation sheet. Okay, and now you can see why it has the same number there as your number. There's so many, that same number of joules there as the charge an electron is in coulombs. It's because they're related by 1 volt. Okay, more formally, potential has this interesting relationship to fields. And it has a relationship to potential energy. So I like to do one sort of SAT analogy type problems. Potential is to potential energy how the electric field is to force. Okay? These guys we've gotten by taking the test charges out of these two. Okay? So there's nothing really mysterious about this. Okay? It's actually pretty standard. The volt itself, or the number of volts in a field, are typically are determined by the big charges around. So if I have a lot of, say, negative charges, okay, and I have some positive charges here, I've set up an electric field like this. It's nice, it's uniform, okay. So the potential difference from here to here, say the number change, the change in voltage, if you like, really only depends on E here, which depends on the charge distribution, and the gap size. Okay, so it's just the geometry of the problem, really. Which means it doesn't matter what kind of particle I send through, this is always going to be the same. So again, we're in a position where if I know the potential difference from one point to another, I can tell you how much energy is being gained. This is actually, it may not seem very useful because you imagine, well, we're probably usually sending electrons around, right? That's true. However, what we're going to find out in a few more days is that the fact that we're sending electrons isn't enough. Because you're also going to want to know how many electrons per second we're throwing down there. And if you use voltage, you can quickly find out how much energy per second is being released. And that's going to be power. That's going to be what we're really interested in most electronics, it turns out. Okay, that's been potential difference. I hope it's been helpful. I will see everybody in class.